You cannot depend on your eyes when your imagination is out of focus. Mark Twain.
So are you ready to have all the mysteries of the particle wave duality of light put to rest once and for all? Well, I'll get to that in a minute, but some of you are still having a lot of questions about that last segment. And that's okay. If you don't know exactly why we're using those equations in the last video yet, don't trip. See, YouTube only allows me 15-minute videos, and I can't possibly fit everything into one clip, seeing as that I'm trying to explain everything from the ground up so that people could understand it even if they don't have prior knowledge of this type of stuff. But I see that there are a lot of people that are really confused about that last video, so allow me to take some time and go back and explain exactly how a two-dimensional photon in the transitional state turns into a three-dimensional capacitor, and why we're using those equations from electrical engineering textbooks and where we got some of these numbers from that were plugged in. But first, I have something to say. People really need to just quit watching my videos if they aren't going to be both appreciative and patient in allowing me to explain everything fully. I mean, it took Frank over 20 years to figure out these math equations and really ponder and realize the implications of his findings. And he spent countless hours on the phone explaining and teaching it all to me. I mean, just tons and tons of hours. And these extremely radical concepts are paradigm shifting, to say the least. And because of this, you can't possibly expect to understand everything fully from a 15-minute video. You know, you might have to watch it a couple times, and you might have to wait for me to explain more, and it'll take much longer than 15 minutes for me to even explain it. So that's not realistic. But the math is also flawless, okay? It's been checked over by a bunch of people already. And the reasoning for the equations used all makes perfect sense when you truly understand what's happening during the quantum transition and what a photon really is. And I'll explain this all in a few seconds, but it does take a while to let it all sink in and to fully understand it. And I want to let you guys know I really do appreciate the constructive feedback and informing me of errors that I make, all that type of stuff, because I want to make this video series as perfect as possible. But people really need to realize that A, I'm only human, and B, I'm doing this for free. And both of these character flaws, as I see it anyway, also applies to Frank. And we really do wish that both of these scenarios weren't the case. And all I ask you is that you allow me ample time to fully explain everything before shouting that it's all BS or attacking me personally. You know, doing that kind of thing just makes me start to think that society doesn't deserve this kind of information. You know, why am I spending all my time on this? Because it's basically turned into a full-time job for me right now, but without a paycheck. And I'm starting to think that progress is only made despite of humanity, not because of it. And Frank's almost lost hope. But I keep telling him that once people truly understand his math, the world will change. And that's my motivation to keep going right now. Maybe I'm just being naive though. Oh yeah, I almost forgot. And if you don't like the music, tough cookies. Hey, if you want to pay me money, hey, I'll put whatever music you want and remake the videos for you. Give me $100. Sucky sucky, me love you long time. Oh yeah, and one other thing. I will eventually show you how to derive the speed of transition, aka the speed of mechanical wave propagation in the nucleus, from first principles. So yes, you really will be able to derive Planck's constant from first principles. But that's a topic for another video. Now, let's really study on the math that I went over in the last segment so you can better understand why a transitional photon is equivalent to a three-dimensional capacitor. Some folks were even so brass as to say that Frank must have just pulled a bunch of random equations out of his ass, boy. But that ain't got no correlation to the real world, especially what be happening during that there quantum transition. That's for sure. Yeah, well, I guess producing Einstein's photoelectric equation without using Planck's constant and both calculating the energy level of an emitted photon by simply knowing the frequency of the photon and simultaneously producing Planck's constant from scratch must all just be a coincidence, right? Please, back on track. The hardest thing to conceptualize is why we're turning a photon, which seems like a two-dimensional ray of light, into a three-dimensional plate capacitor, or how it could even be considered a capacitor at all. Well, a good question is, what is a capacitor exactly? Well, it's a negative and positive potential charge difference, separated by a distance. And what exactly is a photon? It's a wave of light that is alternating between its electric and magnetic components, as we've already talked about, but it's also alternating between a positive and negative electrical charge. Yes, the overall charge of the photon is zero, but it does indeed switch between positive and negative charge states, and the rate at which it switches is what's called its frequency. So a capacitor has a positive and negative charge side, check, and a photon has a positive and negative charge side. Check. The next question you might have is, why are you placing that 0.5 before the distance wavelength in equation 4? Well, a photon is a sine or cosine wave, right? So what's the distance between whenever the wave intersects the zero line on the y-axis? Is it a whole wavelength? No, it's half a wavelength. That means that each half a wavelength, it switches from its positive to a negative. So we already know that a photon is equivalent to a capacitor because they both have positive and negative sides and a distance between them. Now we see that the distance between where it switches from positive and negative and vice versa in terms of a photon is 0.5 wavelengths. So that's why we put the 0.5 lambda in for the D in equation number 4. Get it? However, the most complicated question to answer is, why are we using the wavelength squared as the area of the plates in the capacitor in the equation? You know, a photon doesn't have an area, does it? It's two-dimensional, right? Wrong. A photon is actually 3 dimensions. If you think that you've had your brain melted down and turned into jelly by watching the previous videos, you might want to press pause and grab a damp towel to place on your head before proceeding. You ready? A photon is not simply a two-dimensional line. It's more like a ripple in water. You know, how water ripples when you, I don't know, go skinny dipping, or in my case, go chunky dunking. It has a wavelength from front to back, but it also has a wave width from side to side. Now, I can hear some of you scoffing. You know, the internet transmit that kind of sound. But hear me out. The photon does indeed collapse to what seems like a point-like particle and loses its width, but only once it's absorbed by an atom and slowed to the state of transition. Now, you're probably thinking that it would take nothing short of a superhero to convince you of such garbage. Well, in that case, today's your lucky day.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, When we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern! We fired electrons, tiny bits of matter, through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Okay, yeah, that video was about electrons, not photons, but they act the same way. You don't believe me? You really need to start trusting me more. I feel like our relationship is just based on sex. We never just talk anymore.
To understand the two-slit experiment, we are going to need a new quantum theory on light and time. In this diagram, light will expand in all possible directions as a wave-particle function of quantized wavefronts. When the wave function reaches the screen with the two slits, the photons will react with the electrons of the screen. This will collapse the wave-particle duality of the light, creating new quantum particles in space, and also new moments in time. The part of the wave that does not come in contact with the screen will expand in all possible routes, going through both slits as two light spheres of quantized wavefronts. Constructive and destructive interference between the waves will cause them to superimpose or cancel each other out. When this wave-particle function comes in contact with the screen, it will collapse, creating new moments in time and new quantum particles in the shape of an interference pattern.